Hello and welcome to the presentation of our work titled The Out-of-Distribution Blind Spot of Unsupervised Lesion Detection. Now, before I jump in, I want to sincerely thank all the authors listed below for the great guidance and collaboration throughout the project. Now, why do we aim to perform unsupervised lesion detection on brain MRI data when clearly supervised methods represent the state of the art in terms of segmentation performance? Well, first, unsupervised approaches are free from the need to curate large amounts of labeled data, which in our field is a laborious and expensive process. Second, these methods commend themselves to serve as a general purpose anomaly detection framework without being restricted to specific anomalies seen during training. Now, as you can see, in practice, we might run inference on either healthy in-distribution samples or lesional samples, which are then out of distribution or OOD by definition, since they have not been encountered during training. Furthermore, we will encounter samples which have not been recorded using different scanners or protocols and are thus always OOD, no matter if lesional or not. In summary, we point out that there are hence several reasons for a sample to be OOD. The following depicts our lesion detection framework using a variational autoencoder as it's commonly used. Now, during training, the encoder learns a representation mapping using healthy samples only. And during inference, we perform inference on potentially lesional samples where the model is not expected to be able to reconstruct lesional parts of the brain faithfully. Anomaly detection is then typically performed on the residual map or thresholded version thereof, or in the latent space representation. Below you can see the VAD loss function, which consists of a reconstruction error, and the prior loss, which is the KL divergence between the posterior and prior latent space distributions. These terms, or the full combinations, are commonly used as anomaly detection scores. In this work, we pose the question, or raise the hypothesis, that lesion detection and OOD detection with respect to domain shifts are inherently equated using this framework, which makes such models particularly vulnerable to domain-shifted test samples. We support our claims with various experiments on out-of-distribution and in-distribution test data. And furthermore, we address the challenge of disentangling these underlying causes for a sample to be OOD, building on latest developments in the field of OOD detection, and by proposing an entropy score on the residual map. Now, finally, we answered the question whether histogram matching is a free pass to remedy domain shift effects. So these were the main datasets used throughout the work. Models have been trained using T2 weighted images from the CAMCAN datasets, which hold around 70,000 slices from a couple hundred patients. And since we had no access to a comparable dataset which would include lesional samples, we crafted an artificial lesional test set by adding Gaussian blobs on the in-distribution samples with similar intensities compared to the actual lesions found in other datasets. Furthermore, we tested with histogram matched and non-matched samples from the BRATS dataset and other variants which are clearly OOD to sort of achieve a cascade of datasets which are more and more out of distribution. Now, on the left hand here, we can see what happens when we run inference on in-distribution CAMCAN samples, while on the right, we run inference on BRATS and our modified CAMCAN samples with both similar detection performances, actually. Now, these plots reveal an interesting finding when comparing the loss term distributions from the in-distribution CAMCAN samples in teal and other datasets. Note that it's actually not possible here to distinguish healthy slices from the BRATS dataset, which is OOD, in pink from the artificial lesion samples from the CAMCAN dataset in orange, since contributions from the domain shift are actually equal compared to the impact of the lesions. Now, furthermore, we can see from the bottommost graph that it might be potentially dangerous to rely solely on the KL divergence as an anomaly measure, since samples, which are very OOD, could be mapped in a way resulting in a small KL divergence. As a means to overcome these limitations here and propose a score susceptible to the impact of lesions independently from any domain shifts, we proposed an entropy score on the residual map. Now, the rationale behind this is that the entropy as a measure of uncertainty when interpreting the residual map as a categorical distribution, should distinguish samples which have more spread out reconstruction errors compared to the confined ones originating from actual lesions. Now, unfortunately, we did not really get the desired signal here and have to leave the disentanglement of the factors for future work. Now, to conclude, we point out that unsupervised lesion detection is by very nature of the methodology equated with out-of-distribution detection, making these frameworks vulnerable to domain shift effects. This might be actually of great concern when speaking about clinical applicability. Second, we would like to see datasets containing lesional and non-lesional samples taken with the same imaging protocols for further experiments. And finally, as an idea for future work, due to the underlying principle, and my PC is going to shut down, of unsupervised anomaly detection, little supervision might be actually necessary to learn these different factors for samples to be out of distribution during training. Thank you very much.